Hello and welcome back to our video series on astronomy. It's Mr Nelms from Haberdashers Adams here as part of our physics and astronomy department, and I'll be taking you through our third video in our moon series. Today we're going to look at the key features of the moon and when it's best to observe them.
3, 2, 1.
We choose to go to the moon.
As our closest neighbour in the solar system, the moon is the only object in the night sky which we can distinguish any features of using the naked eye. These features are not particularly clear when viewed like this though. The moon takes up about the same amount of sky as our thumbnail does if we give it a thumbs up at about arm's length, just over half a degree across as an angle. If we are viewing the moon without any assistance, we will be able to distinguish certain features as lighter and darker, but not much more. This led to earlier astronomers thinking that they could see the face of a man on the lunar surface. It is only when we use devices like telescopes that we can start to understand the actual topography of the moon. In the 1600s, astronomers were able to tell that the lighter and darker regions of the lunar surface were not just distinct in colour, but also in texture. However, without sufficient magnification on their telescopes, they misidentified the darker, smoother regions of the moon as bodies of water, leading to their naming of Maria, which comes from the Latin for sea. That meant that by their logic, the lighter, more textured sections must be the land or terre. Since then, the notion of bodies of water on the moon's surface has been well and truly dismissed, though the names Maria and Terre have stuck. We now have a much better understanding of the actual features of the lunar surface and how they formed. To understand the formation of the Maria and Terre, though, we need to look at how craters are formed. This is why we have poured 2 kilograms of flour out into this container, which we're going to use to model the moon's surface. When the moon first formed over 4 billion years ago, its surface was relatively smooth, having solidified from the molten remnants of rock that had just collided with the Earth, we think. However, over the millions of years shortly after this, the moon was subjected to a period known as the heavy bombardment. During this period, the solar system was still thought to be settling into its orbit, with the larger planets causing disruption to the orbits of asteroids as they passed nearby them when they were going in and out of closer orbits with the Sun. This is thought to have led to an increased rate of asteroids colliding with the inner planets, though the astronomy community is currently debating certain aspects of this. As these collisions occurred, they compressed the ground below them, but also ejected material out to the sides. The meteorite itself can be almost entirely vaporized by the collision, especially when impacting on bodies like the moon, which have no atmosphere, so no air resistance, to slow it down before it impacts into the surface at tens of kilometers per second. These impacts continued to happen over tens to hundreds of thousands of years, covering the entire surface of the moon with craters of differing shapes and sizes. If we want to see the details of a crater more clearly, the direction of lighting is important. When lit directly from above, it is hard to see the topography of each crater. What we really want is for the sunlight to hit the crater at a high angle from here. This creates more pronounced shadows and allows astronomers to see the shape and features of each crater much more clearly. Looking at this on our model of the moon, the craters which are easiest to see are those near what is called the terminator. This is the boundary between the parts of the moon that are illuminated by the sun and those which are in shadow. With the light from the sun coming across the rim of craters, this creates sharp shadows so that even observers without a telescope can identify the larger lunar craters from Earth. So this explains the formation of most lunar craters,
but not why the lunar surface would have differing darkness at different points. To understand this, we need to understand that during the heavy bombardment periods, the interior of the moon was still molten following its formation. Therefore, when the moon was subject to repeated impacts, the deeper and larger craters offered routes for this magma inside the moon to reach the surface and cool.
As it emerged onto the lunar surface, it flowed as lava across the crater regions, leaving flat, large areas of basalt. These iron-rich plains look darker than the raised regions where the lava did not reach. These regions have since become known as the maria or seas for the relative smooth appearance. This process seems to have taken much of the moon's history, with its volcanic period only ending around 1 billion years ago. What this also means is that any craters forming on the maria are likely to be significantly younger than a lot of the other craters on the moon's surface, as they will have had to have formed after this volcanic period finished.
Whilst the lava was able to reach the lowlands and fill in these deeper craters, it did not reach the less impacted and higher regions of the lunar surface. These regions were left relatively untouched, barring any later impacts, allowing us to see regions of the moon which have remained unchanged in nearly 4 billion years. These are the terrae. These older rocky surfaces are primarily composed of igneous rocks, formed when the lunar surface solidified after the initial formation of the moon.
That explains the features that we can easily see from Earth with the naked eye. If we look a bit closer using something like a telescope, then there is more to be seen.
One of the features that we can look at are the plentiful rills that cover the lunar surface. These were discovered just over 200 years ago, and the name comes from the Latin rima, which translates as fissures or cracks. The rills can be up to a few kilometres across and many hundreds of kilometres in length. There are two main categories: straight rills and sinuous rills. Straight rills are thought to have formed when parts of the crust have collapsed or sunk along fault lines. These are most commonly seen along crater chains, so if you look with a telescope at the edges of craters, you might spot one. Sinuous rills follow a more curving path and are thought to have formed where lava has flowed along the surface of the moon during its more volcanically active phase, leaving deep channels in the rocks and exposing the different layers under the lunar surface.
Another feature that we can see on the moon are mountainous regions. But unlike on Earth, where mountains form as a result of tectonic activity, on the moon many of them appear to be the ejected material from the largest impacts on the early moon's surface.
The heavily impacted surface of the moon has led to the formation of many mountains and mountain ranges. The highest individual mountain on the moon is Mons Huygens, at a height of around 5,500 kilometres, on the edge of Mare Imbrium.
Now, if any viewers watching this video are undertaking GCSE astronomy, there are 7 specific features that you need to be able to identify on the near side of the moon. These include 3 maria, 3 craters, and 1 mountain range.
The 3 maria that students need to be able to identify are the oceans of storms, Sea of Crises, and the location of the Apollo 11 landing, the Sea of Tranquility. The 3 craters you need to know are Copernicus, Kepler, and perhaps the easiest to spot, Tycho in the south. And finally, the Apennine Mountains, where Mons Huygens can be found.
That wraps up our whistle-stop tour of the lunar surface and features. I hope you've enjoyed this video and potentially learned something new about our nearest neighbour in the solar system. And maybe the next time you see the moon in the sky, you can take a minute to have a closer look and identify some of those key features yourself.
If you want to do something beyond watching these videos, here are 3 questions which can help you push your knowledge further. 1. How do astronomers work out the altitudes of mountains on the moon? 2. what is a wrinkle ridge and how do they form? And 3, why did the Apollo 11 mission choose the Sea of Tranquility as its landing site? Thank you so much for watching, and hopefully you'll join us for our next episode, which compares the near and far sides of the moon and looks at why they are different.